with surprising facts and just enough humor to keep you hooked. Today, we're diving into what many call the holy grail of modern physics. You know, the big one. How to finally bring together Albert Einstein's vast universe of gravity, described by general relativity, with the tiny, kind of quirky quantum world that governs everything at the subatomic level. Yeah, it's the ultimate puzzle for physicists, and it's where our deep dive begins today. We're actually unpacking a really fascinating hypothesis from one of you, our listeners. The core idea is that basically a fundamental particle state is defined by a unique vibrational frequency, and this frequency, well, it dictates its unique location within spacetime. And gravity, the hypothesis suggests it emerges from particles kind of matching or synchronizing their frequencies, which then causes them to draw closer. Yeah. Pretty intuitive, right?
It is intuitive. And our mission today is to systematically analyze this really interesting model against the established laws of physics. Then, crucially, we'll explore how its core intuitions actually resonate with some of the most speculative, really cutting-edge theories out there. We're going to peel back the layers on what frequency and location really mean in quantum mechanics, compare this proposed gravity mechanism with general relativity, and then look for, well, maybe surprising parallels in areas like string theory and this idea of emergent gravity.
Okay, so prepare for a journey into the fundamental physics of our universe, from the kind of blurry world of quantum waves to the warped geometry of space-time. We'll discover how even seemingly simple ideas hold profound implications for our understanding of reality. Okay, let's unpack this. So the hypothesis kicks off with this idea of a particle having a unique location. But from what I understand, when you get down to the quantum level, a particle's location isn't as simple as like pointing to it on a map, is it?
You are absolutely right. That everyday idea, of a definite fixed position for something, it's completely challenged in the quantum world. In quantum mechanics, a particle's state isn't really a single spot. It's described by something called a wave function. Think of the wave function as like a mathematical blueprint containing all possible information we can know about that particle. Now, the tricky part is you can't see this wave function directly. It's not measurable in itself. But there's a rule, the Born rule, that tells us how it connects to the real world. Basically, the square of the wave function gives you the probability of finding the particle somewhere. So where the wave is strongest, that's where you're most likely to find it if you, try to measure it.
Probability. So it's not just that we don't know its position with certainty. It genuinely doesn't have one in the way we usually imagine until we actually look for it. My gut feeling is there must be a tiny little electron somewhere, even if I can't see it. Are you saying quantum mechanics fundamentally disagrees with that intuition?
Precisely. Yes, it fundamentally disagrees. This probabilistic nature isn't just about our ignorance. It's intrinsic to reality at the quantum scale. Before a measurement, a particle exists in what's called a superposition of all possible locations. It's kind of spread out like a wave, a probability cloud. It's essentially everywhere within that cloud at once. Only when a measurement occurs, when you interact with it, does that wave function collapse to a single definite outcome.
Wow.
So right away, the hypothesis's foundational premise that a particle has a unique, definite location determined by some intrinsic property is in direct and really fundamental conflict with quantum mechanics. It assumes a classical deterministic reality for position, the very thing quantum mechanics was developed to replace. This isn't a minor tweak, it's a profound contradiction.
Well, that's a pretty big hurdle right out of the gate.
Oh.
Okay, but let's move to the other key element, this unique vibrational frequency. What does frequency actually mean for a particle in quantum physics? Is that more straightforward?
Frequency is incredibly important, yes, but again, it has several distinct meanings. It's not quite as simple as just one thing. For instance, there's the famous Planck-Einstein relation, E, that directly links the energy of a quantum, like a photon or an electron, to its frequency. Higher frequency simply means higher energy. That's fundamental. Then there's the de Broglie relation. This connects a particle's momentum, how much oomph it has, to the wavelength of its associated matter wave. And wavelength, of course, is just the inverse of frequency, essentially. And even a particle just sitting still at rest has an intrinsic frequency related to its rest mass. We call it the Compton frequency. You can sort of think of this as the natural oscillation frequency of the little ripple in the quantum field that is the particle. So if we try to interpret the hypothesis's unique vibrational frequency in the most, let's say, physically meaningful way, it's basically a proxy for the particle's mass energy. A particle with more mass or more energy would just have a higher intrinsic frequency.
Okay, that seems to fit the spirit of the hypothesis reasonably well. Like, different particles have different fundamental frequencies based on their mass. But does this interpretation create new conflicts when we bring gravity into the picture.
It does, almost immediately. It leads to a direct conflict with one of general relativity's key predictions, gravitational time dilation. This is the well-tested idea that clocks run slower, which means any oscillator, anything that vibrates, has a lower measured frequency and stronger gravitational field.
Right, like near a black hole, time slows down.
Exactly, or even just closer to the Earth's surface compared to higher up. This isn't just theory, it's been confirmed by experiments like Pound-Rebka, and it's absolutely crucial for things like GPS satellites to function accurately. They have to account for this time difference. Now, the hypothesis suggests frequency matching for particles in stronger gravity. That implies frequencies should converge, become more similar. But general relativity predicts the exact opposite. Gravity creates a gradient of frequencies. Frequencies are actually lower where gravity is stronger. They diverge, not converge. Ah, okay. So they predict opposite effects.
Precisely. And this highlights a deeper conceptual issue, really. The established understanding in physics follows a kind of chain. Mass, or energy, which relates to frequency, influences space-time curvature, and that curvature then guides the probabilistic motion of particles. The hypothesis, however, seemed to try and bypass that whole middle step, the space-time geometry. It suggests a direct link from particle frequency to its exact location, which, as we've seen, clashes with quantum mechanics, and now we see it clashes with general relativity too.
Wow. Okay. So the quantum world rejects the fixed location idea, and general relativity rejects the frequency matching idea for gravity. But there's more, isn't there? You mentioned something about Heisenberg. This feels like the real nail in the coffin for this specific link between frequency and location. What exactly is the Heisenberg uncertainty principle? Yes, this is probably the most fundamental obstacle. Formulated by Werner Heisenberg, this principle states a fundamental, absolutely inescapable limit to the precision with which certain pairs of properties can be simultaneously known. The classic example is a particle's position, where it is, and its momentum, where it's going, essentially related to its frequency. There's a mathematical inequality, Suftor2. Basically, it means the product of the uncertainties in position and momentum can never be smaller than a certain tiny fundamental constant. You can't know both perfectly. If you know one very precisely, the other becomes inherently fuzzy.
Okay, a fundamental fuzziness. So how does this relate directly to the hypothesis's idea of a unique vibrational frequency defining a unique location? Because the hypothesis states that one directly leads to the other.
Right, and this is where the hypothesis completely breaks down. A unique vibrational frequency, mathematically speaking, means a perfectly defined frequency. That corresponds to a perfectly defined wavelength, and therefore, via de Broglie, a perfectly defined momentum. Zero uncertainty in momentum.
Okay, perfect frequency means perfect momentum.
Exactly. Now think about a wave with a perfectly defined frequency, like an infinite pure sine wave stretching across the entire universe. Where is that wave?
Oh, everywhere.
Precisely. A core property of the mathematics linking position and momentum, called the Fourier transform, tells us that a wave with perfectly defined momentum, zero uncertainty, must have an infinite uncertainty in position. Such a particle is completely delocalized. It has an equal probability of being found literally anywhere in the universe.
So the exact opposite of a unique location.
The exact opposite. To get something approximating a unique location, to make a particle localized in space, you must combine or superimpose a broad range of different frequencies and momenta. Think of making a sharp pulse on a rope. You need lots of different wave frequencies added together to make that sharp peak. The more tightly you want to confine the particle, the wider the range of frequencies it must possess. So this reveals a really profound and frankly fatal flaw in the hypothesis as stated. It claims a unique frequency defines a unique location. The Heisenberg uncertainty principle dictates the precise opposite. A unique frequency implies a completely non-unique, infinitely delocalized location. The hypothesis isn't just slightly off, it represents a perfect inversion of a fundamental quantum principle. The state it describes is mathematically and fundamentally impossible in our universe.
Okay, that truly drives the point home. The uncertainty principle isn't just a hurdle, it's like a fundamental law saying, nope, can't do that. The specific mechanism proposed is mathematically ruled out. But here's where our deep dive gets really interesting. Even when a specific idea like this one doesn't hold up to scientific scrutiny, sometimes the underlying intuition can still point towards profound truths or interesting areas. Let's explore that intuition now, maybe by looking at gravity through Einstein's eyes and then diving into some of the more out there ideas in physics. Let's pivot back to gravity then. The hypothesis proposes frequency matching mechanism. How does Einstein's general theory of relativity, our best theory of gravity so far, explain what gravity actually is?
Right. General Relativity, or GR, published back in 1915, was just revolutionary, a complete paradigm shift. Newton saw gravity as an invisible force, like magnetism, acting across space, pulling things together. Einstein proposed something radically different. He said gravity isn't a force in spacetime, it's an intrinsic property of spacetime itself. It's what happens when spacetime, this unified four-dimensional fabric, gets curved or warped by the presence of mass and energy. There's a great quote from physicist John Archibald Wheeler: "Spacetime tells matter how to move. Matter tells spacetime how to curve." That's the essence of it. Mass and energy actually change the geometry of spacetime around them. And objects, like planets or light rays, then simply follow the straightest possible paths, we call them geodesics, through this curved geometry. A planet orbiting the sun isn't being actively pulled by a force. It's following its natural, straightest path through the spacetime that the sun has curved, kind of like a marble rolling around the warped surface inside a heavy bowling ball placed on a rubber sheet.
So it's about the shape of space and time, not particles talking to each other through frequencies.
Exactly. This geometric interpretation is fundamentally different from the hypothesis. The hypothesis sounds more like an active, force-like interaction, maybe implying direct communication between particles to match frequencies. GR is much more passive, you could say. It's geometry-based. Objects just respond to the local curvature of space-time right where they are. There's no spooky action at a distance, just local geometry.
But the language we sometimes hear in modern physics about space-time vibrating or having frequencies, maybe that's what inspired the hypothesis. What exactly are gravitational waves and how do they relate to frequency? Because that sounds like vibration.
That's a great point, and it's easy to see how that language could lead to confusion. Gravitational waves, predicted by Einstein way back in 1916 and then stunningly detected directly by LIGO and Virgo starting in 2015, these are not waves of particles traveling through space-time like light waves or photons traveling through space. Instead, they are propagating ripples in the fabric of space-time itself. They're actual stretches and squeezes of space and time generated by incredibly violent cosmic events like two black holes merging or neutron stars colliding.
So space-time itself is waving.
Exactly. And the frequency of a gravitational wave is determined by the macroscopic dynamics of the source. For instance, as two massive black holes spiral closer and closer, they orbit faster and faster, emitting gravitational waves that sweep upward in frequency, creating that characteristic chirp signal LIGO heard. The frequencies we detect with LIGO are typically quite low, relatively speaking, in the range of tens to maybe a few hundred hertz. Audible frequencies if they were sound waves.
Okay, so that's very different from...
Vastly different from the intrinsic Compton frequency of a fundamental particle. For something like an electron, that frequency is astronomically high, like 10 to the power of 20 hertz. Way, way higher. So the hypothesis seems to be conflating these two completely different types of frequencies. It's sort of mistakenly applying a property of a large-scale classical wave, a gravitational wave, to the intrinsic quantum properties of individual particles. Different phenomena, different scales, different frequencies altogether.
Got it. Okay, so GR describes gravity as geometry, and its waves are ripples of space-time, not related to particle frequencies in this way. How well, then, has general relativity actually been tested? What's the kind of empirical standard any new theory of gravity would have to meet?
Oh, GR is one of the most rigorously and precisely tested theories in all of science. It's stood up to incredible scrutiny for over a century now. Any alternative theory, any new idea about gravity absolutely must reproduce all of GR's successful predictions with the same, frankly, extraordinary accuracy. If it can't, it's basically dead on arrival.
So what are some of those key tests?
Well, GR didn't just explain one little thing. It nailed a whole host of observations. It perfectly accounted for that tiny extra wobble, the anomalous perihelion precession, in Mercury's orbit, something Newtonian gravity just couldn't explain. That was about 43 arcseconds per century, and GR got it spot on. It predicted the bending of starlight by the sun's gravity, sort of famously confirmed by Arthur Eddington during a solar eclipse in 1919. Modern measurements confirm that deflection to about 0.03% precision. It accurately describes gravitational redshift light losing energy as it climbs out of a gravity well. We see this in light from dense stars, and it's tested here on Earth, and as we said, it's vital for GPS. There's the Shapiro time delay radar signals taking slightly longer to travel near a massive object like the sun. The Cassini spacecraft confirmed this effect to about 0.002% precision, I believe. Astonishing. Then you have binary pulsars, like the Hulse-Taylor pulsar. These pairs of neutron stars orbiting each other lose energy exactly as GR predicts they should, by emitting gravitational waves. Their orbits decay, perfectly matching the theory that earned a Nobel Prize. And of course, the most dramatic confirmation, the direct detection of gravitational waves by LIGO and Virgo. The specific chirp waveforms they measured from merging black holes and neutron stars are an almost perfect match to the predictions made by solving Einstein's equations on supercomputers. It's just incredibly successful.
Okay, that's a very, very high bar.
It is. And the hypothesis is sort of qualitative frequency matching model.
Right.
It offers no clear mathematical framework to even begin generating these precise quantitative predictions. To be taken seriously, a theory needs that mathematical consistency and predictive power.
Right. So given these fundamental conflicts with both quantum mechanics and GR, and the incredible success of GR, is there any validity, any echo of the core intuitions behind this hypothesis within the wider landscape of modern physics, or is it just completely off base?
No, not completely off base at all. And this is the really interesting part. While the hypothesis's specific answers, the mechanics it proposes, are inconsistent with established physics, its underlying intuitions, they're actually quite profound. The idea is that maybe vibration is fundamental to matter, that gravity might arise from some deeper principle, that a particle's properties are somehow tied to its place or role in the cosmos. These intuitions are actually at the very heart of some of the biggest questions in research programs in modern physics. In fact, there's a highly speculative research paper out there that explores a strikingly similar conceptual framework. It actually tries to derive quantum properties of matter, like mass, from a classical theory of space-time itself. Its core ideas include associating a particle's rest mass with a kind of quantized vibration in its own proper time. It's personal clock, if you like. And its total energy is linked to a specific frequency coming from a sort of underlying space-time wave. The goal is explicitly to show mass and energy emerging from space-time properties.
Wow, so someone is actually trying something conceptually similar.
Yes, exactly. It shows that our listener's idea isn't totally out of left field. It's like a folk physics version of a known, though admittedly niche and incredibly challenging, research direction. It validates the core intuition, but it also highlights the immense leap needed to turn that intuition into rigorous, consistent mathematics.
Okay, that's fascinating. And the idea that vibration is fundamental.
Yeah.
That immediately makes me think of something else I've heard about.
String theory. Absolutely. String theory, which is still one of the leading candidates for a theory of quantum gravity, takes that intuition vibration is fundamental to its logical extreme. In string theory, the fundamental constituents of reality aren't point-like particles. They're tiny, one-dimensional vibrating filaments of energy called strings, like unimaginably small guitar strings. And the different ways these strings can vibrate, their different modes of vibration, manifest as all the different elementary particles we see. One vibrational pattern might look like an electron, another like a quark, another like a photon. So the particle's properties, its mass, its charge, its spin, are all determined by its music, by the specific way its string is vibrating.
And gravity fits in there somehow.
Crucially, yes. One particular vibrational mode of a closed loop of string corresponds precisely to the properties expected of the graviton, the hypothetical quantum particle that mediates the gravitational force. So gravity isn't just added on, it's an unavoidable, inherent part of string theory. This provides a really compelling parallel to the hypothesis' intuitive link between vibration and identity. But the implementation is vastly different. In string theory, gravity is a quantum force mediated by these graviton vibrations, not some kind of classical frequency matching causing attraction.
And the location problem.
Right. And importantly, even in string theory, a string vibrating in the mode that corresponds to an electron still doesn't have a definite unique location. Its position is still probabilistic, governed by the rules of quantum mechanics, including the uncertainty principle. String theory builds upon quantum mechanics. It doesn't replace that core aspect.
Okay. This whole discussion also brings up another really big question that seems very active in physics right now. Is gravity actually a fundamental force like electromagnetism? Or could it maybe emerge from something deeper, something more fundamental?
Yes, that's a huge area of research, the emergent gravity paradigm. It's the idea that gravity, and perhaps even space-time itself, isn't fundamental in the way we usually think. Instead, it might arise from the collective behavior of some more microscopic underlying degrees of freedom, much like, say, temperature isn't a fundamental property of a single molecule, but emerges from the average motion of many molecules in a gas or liquid. Or how the fluidity of water emerges from the interactions of individual H2O molecules.
So gravity could be like thermodynamics, an average effect.
Something like that, yes. A prominent example is the idea of entropic gravity, proposed by Eric Ferland. It suggests gravity isn't a fundamental force, but an entropic force, arising from statistical tendencies related to information and entropy, possibly linked to the holographic principle. This whole line of inquiry, asking if gravity comes from something else, resonates very deeply with the spirit of the listener's hypothesis, the idea of deriving gravity from a different underlying physical process. It absolutely validates the question being asked. However, these emergent gravity theories are usually grounded in very abstract concepts like quantum information, entanglement, thermodynamics, not really in simple mechanical frequency oscillations of particles themselves.
Still, the underlying quest is similar.
It is. And finally, just briefly, it's worth mentioning an alternative interpretation of quantum mechanics itself. The pilot wave theory, sometimes called de Broglie-Bohm theory, unlike the standard interpretation we've been discussing, pilot wave theory is actually deterministic. It says particles do always have real, definite positions, even when we're not looking.
Ah, so that sounds closer to the hypothesis.
In that it posits a definite location, yes. But crucially, in pilot wave theory, the particle's definite position is guided by the wave function, or the pilot waves, like a piece of driftwood being guided by the currents in a river. The particle is a separate thing that surfs its associated wave. So while it offers a definite location, that location is not determined directly by the wave's frequency in the simple way the hypothesis suggested. It shows that even quite radical interpretations of quantum mechanics don't necessarily support that specific frequency-to-location mapping.
Okay, so we've explored quantum fuzziness, space-time geometry, vibrating strings, emergent ideas. Where does this leave us with the original hypothesis? Putting it all together. Well, in the final assessment, the hypothesis, as it was presented, unique frequency determines unique location, and frequency matching causes gravity, is unfortunately untenable when confronted with established physics. It's invalidated by really foundational principles of both quantum mechanics, particularly the Heisenberg uncertainty principle, and general relativity. And these theories are supported by, a century of overwhelming experimental evidence. Just to recap, the core mechanism, unique frequency determines unique location, is in direct, stark opposition to the uncertainty principle. A unique frequency mathematically implies infinite spatial delocalization, the precise inverse of what the hypothesis proposed. And its frequency matching idea for gravity is completely incompatible with general relativity's geometric description, which, as we discussed, has been verified to extraordinary precision across an enormous range of phenomena, from Mercury's orbit to black hole mergers.
So scientifically, it doesn't work. But you also said the intuition behind it was powerful and resonates with cutting-edge physics. How do we square that? For someone maybe really attached to this idea, is it just a dead end on that specific point, or?
That's the crucial takeaway, I think. To simply dismiss the inquiry as wrong would be to miss its deeper significance. Yes, the specific mechanism proposed is flawed, but the hypothesis, though incorrect in its execution, seems born from a set of remarkably insightful intuitions. Intuitions that really do resonate strongly with some of the most advanced and profound ideas in modern physics, like the notion that the essence of matter might fundamentally be vibration, that's central to the Planck-Einstein relation and, of course, string theory. The intuition that a particle's properties are somehow deeply tied to its role or place in the cosmos, that's fundamental to our understanding in both quantum mechanics and general relativity. And the feeling that gravity as we experience it, as described by GR, might not be the final word, but could be an emergent phenomenon arising from something deeper, that's exactly what drives research in emergent gravity. So in essence, the hypothesis asks precisely the right kinds of questions. The questions that really animate the search for a unified theory, for a deeper understanding, even if the specific answers it offered are inconsistent with what we currently know and have experimentally verified.
That makes sense. It highlights the difference between a good question and a correct answer. And it raises another important point. What does it actually take for a bold new idea, like this one was trying to become a viable, accepted scientific theory? What are the key requirements?
That journey from a neat concept or intuition to a viable scientific theory is incredibly demanding. It requires several crucial steps. First, mathematical formulation. The ideas have to be translated into precise, unambiguous mathematics. Physics runs on math. Without that, it's hard to make concrete predictions or even check for internal consistency. Second, correspondence and verification. A new theory must, at a minimum, reproduce all the successful results of the existing theories it aims to replace, at least within the domains where those older theories worked. So a new theory of gravity must give you Newtonian gravity back in everyday situations, and it must pass all those stringent tests of general relativity we talked about.
It has to explain the old stuff, too.
Absolutely. And third, it needs to make new falsifiable predictions. It has to predict something novel, something specific that hasn't been observed yet, which experimenters can then go out and test. And crucially, there must be a way the theory could be proven wrong by an experiment. That's falsifiability. The listener's hypothesis, while conceptually interesting, really stumbles at the first hurdle. Its core premises are fundamentally incompatible with the mathematical frameworks of quantum mechanics and GR, preventing it from even getting to the stage of reproducing known results, let alone making new, testable predictions.
Okay, so it's a tough road for any new idea. This deep dive wasn't just about evaluating one specific hypothesis then. It really became about understanding the scientific process itself, how ideas are tested, why consistency matters, and the high bar for overturning established theories. It's actually a great affirmation of curiosity and the sheer power of asking fundamental questions, even if the first answer isn't right.
Exactly. The proposed model isn't a viable scientific answer as it stands, but it represents an excellent question. And asking those kinds of fundamental questions, why is the universe the way it is? Could it be different? What underlies gravity or quantum mechanics? That's the essential first step on the long, challenging, but ultimately rewarding path toward a deeper understanding of the universe.
It makes you wonder, doesn't it? What fundamental assumption in physics might we be holding on to today, maybe completely unconsciously, that future discoveries will reveal to be just as limited or flawed as, say, Newton's idea of absolute space, or the classical intuition that a particle must have a definite location before we measure it? What current huge puzzle, like unifying gravity and quantum mechanics, might require an equally bold, maybe initially counterintuitive conceptual leap to finally crack? We've journeyed today through the probabilistic clouds of the quantum world, the beautifully curved geometry of space-time, and even peered into the speculative landscapes of vibrating strings and emergent realities. And this entire journey, this whole conversation, really began with precisely that kind of bold, creative thought from one of you. Keep those questions coming.